Hi, welcome to a new lecture on Foundations for Machine Learning, and we are continuing to learn linear algebra. This forms one of the biggest mathematical pillars or foundations for the entire machine learning journey for you. So, in the last lecture, we saw how if a matrix is multiplying with a vector, how it transforms the vector. So, essentially, we can look at a matrix as a vector transformation or linear transformation. In this lecture, we will of course be doing a little bit of recap of that so that in case you haven't followed the last lecture, you can still understand what is going on in this lecture completely. And in addition to that, we will also see if one matrix is multiplying with another matrix, how does that translate into a composite linear transformation? So we'll be learning both of this. We will also do a small recap on how to track where a vector ends up after transformation by simply tracking what happens to the initial unit vectors I and j. So welcome to today's lecture. So as we have been mentioning in this course, linear transformation is nothing but it's a function. It's a function that transforms a vector v into another vector v prime, let's say. And how do we express this linear transformation? Linear transformation can be expressed in the form of a matrix. So throughout this lecture, we'll be looking at a two-dimensional plane. So the transformation vector will be a 2x2 matrix. A transformation matrix will be 2x2 in dimension, and the vector will have only x and y dimensions. So if a vector is multiplied by a matrix, it transforms the vector. So let us have a look at two examples. We looked at this in the last lecture, but I just wanted to give you a small recap. So first, let us look at rotation transformation. Imagine that the transformation that is happening to any vector in a given xy space is rotation by 90-degree counterclockwise. So I will just write that here, 90-degree counterclockwise. So this is the vector that we are looking at, vector v. We just want to know what happens to this vector, or where does this vector end up after rotating by 90-degree in counterclockwise. We can also define some actual coordinates. So maybe for ease of writing, I'll keep this vector in such a position such that this is the length of this is 1 x-axis, this is 2, and this is 1. So this green arrow is nothing but the j unit vector, and this blue one is I unit vector. So before looking at what happens to v, we all know what happens to v because we can directly rotate it by 90-degree counterclockwise and see what happens to v. But let us look at it a bit formally. So what will happen to v after a transformation that rotates it? So for that, let's first look at what happens to I and j. So when I rotates by 90-degree, I will end up here. And j, if it rotates by 90-degree, it will end up here. So this will be the new j, and after transformation, and this will be the new I after transformation. Not able to, yeah, this is the new I. So what we have learned is that we can represent the new transformed vector in terms of the new transformed unit vectors I and j. So previously, before transformation, v was expressed as like this, v equal to 2 times I plus 1 times j. And what does transformed v look like? So v transformed I will denote by vt. The transform v should look like, again, these scaling factors should remain the same. 2 times the transformed I plus 1 times the transformed j. So jt. So this is how transformed v should look like. So what is transformed I? Transformed I is nothing but the coordinates of transformed I is 0, 1. So this is how the transformed I vector looks like. What about the transformed j? Transformed j look like -1 0. So the transform v is nothing but the same scalar multiple. So previous scalar multiples were 2 and 1. So I was multiplied by 2, j was multiplied by 1. Now also that will remain the same. But this time the scalar multiple will scale the transformed I vector and transform j vector. So 2 times this guy plus 1 times this new transform vector. And this is nothing but 0, 2 plus -1 0. And this is nothing but -1 2. So where is -1 2? -1 2 is this. We can take a copy. I'll just duplicate this, and -1 2 means x-axis should be -1, y-axis should be 2. So something that looks like this. And you can see that they are almost, the way I have drawn it, you can see it's pretty much perpendicular to each other. So this is how 90-degree transformation, 90-degree rotation works. So here, what is the transformation vector? Transformation matrix. The transformation matrix is expressed in the form of the final location where the and𝑗 lands after transformation. So where did I land after transformation? I landed at 0, 1. It was originally at 1, 0, but now it landed at 0, 1. And j was originally at 0, 1, and it landed at -1, 0. So this is the transformation formation matrix. So this is how we can represent the transformation of this vector v. And how do we get the final transformed vector vt using this transformation matrix? All we need to do is multiply this transformation matrix, multiply this vector with the transformation matrix. So let us do that and see if we are indeed getting this v transformed. So 0, 1, -1, 0 multiplied by the coordinates of the original vector v, which was 2, 1. So this will be 0 multiplied by 2 is 0, -1 multiplied by 1 is -1. Then 1 multiplied by 2 is 2, 0 multiplied by 1 is 0. So this will be 2. So you can clearly see that the transformation matrix can be represented in terms of the first column of the transformation matrix is literally where the I unit vector ends up. The second column of the transformation matrix is where the j unit vector ends up. And the transformation itself is nothing but multiplication of this matrix M, let's call it this as M, with the vector V. And this will give us the transformed vector Vt. And you can see that whatever we calculated here, this -1, 2 for Vt is same as whatever we calculate here after matrix multiplication. So this is an example of a simple linear transformation called rotation. And this rotation can be represented by this matrix 0, 1, -1, 0. So here we just did one transformation, right? That is why the vector v was simply getting multiplied by one matrix. Before moving on to matrix multiplied by another matrix, let's look at one more example. And that example will be that of shear. And then we will look at a composite operation. So in shear, we are not rotating the entire vector or the entire space, but rather we are performing an operation that you must have seen like this. So if this is a body, the way in which this will get sheared is such that if you are pushing it here, the bottom part of this body will remain wherever it is. And this will move like this, right? So this is shear. So in shear operation, this x-axis component will remain the same. So this will stay wherever it is, and this will move here a little bit. So what I can do is I can define the shear operation by saying that the y-axis should get tilted by maybe 45 degree. So what that means is this guy should end up along this, right? And the I component will remain the same. So this is I, and This is I transform. After transformation, I remains wherever it is. This is j transformed. So let's say the transformed value of I is 1 0, which is same as the original I, and the transformed value of j. So this is not a unit vector anymore, so I don't have to put that cap. But transform value of j is, let's say, 1 1. I'm not normalizing it. So it will be 1 1. But if I want to put it as a unit vector, I have to divide by square root of 2, because the magnitude of this vector is square root of 2. And now we just want to see where the actually I should divide by square root of 2, because this unit vector's dimension, we are just performing. Yeah, actually I don't have to keep the magnitude as 1. It can be anything. Magnitude of this vector can be anything. But what we want to see is, if this transformation is applied, what would happen to this particular vector, and how is it represented as a matrix? That's what we want to see, right? So this vector v was originally at x coordinate was 2, y coordinate was 1, and actually this vector was here, over here, something like this, right? So this is how the vector was. And now we just want to see where the vector ends up. So v transformed is nothing but 2 times I transformed plus 1 times j transformed. So, and why is this the case? That is because the original v was simply 2i plus 1j. So the scaling factor 2 and 1 will remain the same, just like what we explained in the rotation transformation. And now we can, since we know the transformed I and transformed j, we can calculate what happens to the vector v after transformation. So the vector v will become this 2 times 1 0, because transformed I is 1 0, plus 1 times 1 1. And this is 2 0 plus 1 1, which is equal to 3 1. So this is the new location of the vector. So if I just draw the axis points 1, 2, 3, the new vector after shear transformation will look something like this. Here shearing happens. And now how do we describe this shear operation in terms of a matrix? The shear operation in terms of matrix is nothing but the first column is where I ends up, second column is where j ends up. So I was exactly where it was. So it was at 1 0. J ended up at 1 1. So now this is the shear operation. So this is the matrix M that represents the shear operation, this particular shear operation that we were talking about. And how do we calculate the transform vector Vt just using this matrix and the original vector V? All we need to do is multiply the vector V by this matrix M. So the vector V was 2 1. So now let's calculate 1 times 2 plus 1 times 1, which is 2 plus 1, that is 3. 0 times 2 plus 1 times 1, that is 1. So this will be 3 1. So this was the vector V, and this is the transformed vector. And you can see that the transform vector which we calculated by this approach is literally same as what we calculate using matrix multiplication. So this again shows that shear operation as a linear transformation can be simply be represented by a matrix multiplication. So here the input vector is this, output vector is this, and this is what is happening to the input vector. It is getting multiplied by this matrix M. So it's almost like a function. Now let's look at an interesting case. What if we are applying first rotation and then shear? So we are not just doing shear, or we are not just doing rotation. We are not performing only one operation. We are operating two operations, but one after the other. Let's see what happens in that case. So first, I want to maybe copy paste. Okay, I already have it here. I just wanted to start with the vector v. So the vector v originally was this, right? It was originally at 2 1. So this is x-axis coordinate is 2 and y-axis coordinate is 1. So let me just write that down. Now, what happens to this vector if we rotate it by 90-degree clockwise, counterclockwise? It ends up becoming something like this. So here, this will be -1 and this will be 2. So after rotation, so let's say vector v after transformation tr, so tr for rotation transformation will be -1, 2. So we saw this earlier. So I'm just writing down the final position of the vector, right? And then we were applying the shear transformation. So let's say sequentially, we are doing 2 steps. One is rotate by -90 degree. So here by -90, for minus, I'm just using counterclockwise, plus means clockwise. We can use any notation, does not matter. Then shear. So we did rotate by 90 degree counterclockwise, that is this. Now, how do we apply shear? We apply shear by multiplying with this matrix. So shear matrix was nothing but 1, 1, 0, 1. So matrix for shear was 1, 1, 0, 1. And matrix for rotation MR, this was this over here, 0, 1, -1, 0. 0, 1, -1, 0. So this was rotation matrix. And we could have gotten this, like we know that the final vector that we get after rotation transformation is nothing but the rotation matrix. You multiply that with the original vector, right? So, and how do we calculate this? Simply 0, -1, 1, 0 multiplied by 2, 1. This is equal to -1. So 0 times 2 plus -1 times 1 plus 1 times 2 plus 0 times 1. So this is 2. So that is exactly what we have already gotten here. Now, what if we want to shear this vector? So if we want to shear this vector, it's simply the final transformed vector is nothing but whatever we have after rotation transformation. On top of this, we will multiply with this matrix, the shear matrix. So what is this? 1, 1, 0, 1. This matrix multiplies with -1, 2. Because -1, 2 is the vector after just the rotation transformation. And this becomes 1 times -1, which is -1, plus 2, that will be 1. 0 times -1 is 0. 1 times 2 is 2. So this will become 1, 2. So what does 1, 2 look like? So 1, 2 will look like something like this. 1 along x-axis and 2 along y-axis. So this is, now I can simply denote. So this was the original vector, right? This is 2, 1. This was the vector after rotation transformation. This was -1, 2. And this is the vector after rotation and shear. So VT, rotation and shear. VT for transformation, R for rotation, S for shear. This will be 1, 2. So that is exactly what we calculated here. Now I have an interesting question. So if we are sequentially applying rotation first and transformation next, is it similar to multiplying the original vector V by 2 matrices? So what I mean by that is the transformation after rotation and shear, is this equal to the matrix for, so first it was matrix for, so we are transforming the vector V. First we multiply it by matrix for rotation and then we multiply by matrix for shear. So is this valid? If that is the case, can we denote this by one single matrix, let's say MSR? So S for shear and MRS. Because we are reading this from right to left. So in if we are multiplying a vector with a matrix and then that whole thing with another matrix, we first do the matrix multiplication of this matrix with this vector, and then the result is being multiplied by this. So this whole thing is like a composite operation. It's a composite of two linear operations. The first linear operation is rotation, second linear operation is shear. So here when I write, instead of writing MSR, I'm writing MRS because this matrix does a rotation transformation followed by a shear transformation. So is this true? We can see that by actually calculating the product of this matrix. So our rotation matrix was this. So 0, -1, this is rotation matrix. And our shear matrix is 1, 0, 1, 1. 1, 0, which one is 0? The bottom one is 0, 1, 0, 1, 1. So this is MR, and this is shear, and this is rotation. So if we multiply these two matrices, what do we get? We get 1 times 0 plus 1 times 1, that is 1. That is the first element. So first of all, what should be the output dimension? This is 2 by 2, and this is 2 by 2. So if we multiply 2 by 2 matrices, output is also 2 by 2. Then this will be 1 times -1 plus 1 times 0. So that will be -1. Then we have 0 times 0 plus 1 times 1. So that is 1. And then we have 0 times -1 plus 1 times 0. This is 0. So this is the composite matrix, which is a matrix that denotes first rotation and then shear. But my question is, if we multiply the original vector v, which was actually 2, 1, right? If we multiply this vector by this composite matrix, will we get this vector as the output? Because final vector after rotation and shear was this guy, 1, 2. We can test that actually. So let's see. So 1 minus 1, 1, 0, which is this guy, is multiplying with the vector v, 2, 1. So now this is the composite matrix that shows rotation plus shear, and this is the original vector v. And what is this? 1 times 2 plus -1 times 1, that is 1. And 1 times 2 plus 0 times 1, that is 2. So now this is the vector that we are getting after, this is the transform vector after rotation and shear. So 1, 2. Is this the one that we got before? Let's see. It was 1 and 2. X-axis component was 1, y was 2. So what does this show? This shows that the product of two matrices like this is nothing but it's a composite linear transformation. So the composite matrix basically performs two linear transformations back to back. So if you see that a vector v is multiplied by simply a matrix, this, let's say, rotation, this is just a single linear transformation. But then if this whole thing, if this is again multiplied by another matrix, shear, now this combined thing is actually sequentially applying first rotation and then shear. So the product of these two matrices, in this way, we can view as a composite linear transformation. An individual matrix we can view as just a single linear transformation. So we saw an individual matrix for shear over in the above part, like we performed shear. So this individual matrix 1, 1, 0, 1 was denoting shear operation. This individual matrix 0, -1, 1, 0 was denoting individual shear rotation operation. And this composite matrix, which is the product of MS and MR, and the value was 1, -1, 1, 0, this denotes two sequential operations, first rotation, second shear. So what we learned here is a vector can be transformed by a single matrix multiplication, and an individual matrix we can see as a linear transformation. And if this matrix is multiplied, if this matrix is multiplying with a vector, then what we are doing is transforming the vector. But what if the matrix is multiplying with another matrix? Then that is basically definition of a composite linear transformation. So the resultant matrix, which comes because of the product of two other matrices, essentially does the composite function. And here, what is the composite function that it performs? It's nothing but simultaneously applying rotation and shear. Now let's do one more thing. So this will be the last thing that we will look at in this lecture, which is calculation of where the vector finally lands, right? So we had the original vector v equal to, this was 2, 1. I'll copy paste the graph once again because I'll need this. Okay, so this is the vector v, and let me put the I and j here. Okay, so this is vector v. So now can we do the following? If this vector v is being multiplied first by the matrix corresponding to rotation, which was 0, 0 along the diagonal and 1 minus 1 along the other diagonal, 1 minus 1, 0, 0, and then shear. So shear was 1, 1, 1, 1, 0, 1. So from this, let's look at it sequentially, right? So first, when this operation is being performed, something is happening to the vector v. And where do we know? How do we know where this vector v is going to end up? We know that by tracking what happens to the unit vectors. So originally, when we are starting the linear transformation, the unit vectors are going to end up somewhere. And how do we know where is that going to end up? The unit vectors, where the unit vectors end up are the first the first column and second column. So first column is where the unit vector I is going to end up. Second column is where the unit vector j is going to end up. So if the original vector was denoted by 2i plus 1j, then after the rotation transformation, the new vector vtr, v transformation rotation, is nothing but 2 times whatever is the vector I after rotation transformation. This may be unit vector, may not be unit vector, depends on the operation, plus 1 times the wherever the j unit vector ends up after rotation transformation. And where is that? That is 2 times this guy, 0, 1. The first column of the first linear transformation matrix is where the unit vector I ends up. So that is 0, 1, plus second column of the first linear transformation matrix is where the unit vector j ends up after rotation. So that is 1 times minus 1, 0. So what is this? This is 0, 2 plus minus 1, 0 equal to minus 1, 2. Right? So this is where the vector v ends up after rotating the first starting vector v. Now one more thing. After we apply this transformation, so we have now one more transformation, right? So this transformation will transform the new unit vectors also. So the new unit vectors were at 0, 1 and minus 1, 0. So this matrix will transform them. So let's see what happens to those unit vectors. So this 0, 1, this guy 0, 1 will end up at 1, 0. So let me recap. Let me take a moment to pause. And in case you are not following, let me show you what I mean. After the first rotation transformation, the unit vector I and j will end up at here and here respectively. So the first column is where unit vector I ends up. Second column is where unit vector j ends up. Now something is happening again, because what is that transformation? There is a shear transformation happening, which will again change where the unit vector will land. And how do we know where the new unit vector is going to land? The new unit vector is going to land at 1, 0. So this will be the new unit vector I, and this will be the new unit vector j. So the new unit vector I will be at 1 0, and the new unit vector j will be at 1 1. And this is after the result of this transformation. So after rotation, we had something like this: -1 times I plus 2 times j. So this is what we had after the first transformation. Now the scaling factor will again remain the same. It will be -1 times I plus 2 times j. So after changing the unit vector to the new position, where this is the new position of I and this is the new position of j, this will be scaled by -1 and this will be scaled by 2. So what would that be? That will be -1 0 plus 2 2. This will be nothing but 1 2. And is 1 2 the final position of the vector after the composite transformation? It is. This is the final position of the vector after composite transformation. So what we did here is we first tracked what happens to the unit vector initially after the first transformation, and we saw that firstly the unit vector transforms to unit vector I transforms to 0 1 and j transforms to -1 0. Based on that, we calculated where this vector v will land after rotation, and based on that, we found that the new place where it lands is this -1 2. And this -1 2 can be again expressed in terms of the original I and j. And what is that? That is nothing but -1 times I plus 2 times j. Now again, we are applying one more transformation, and as a result of that transformation, this I and j is again going to change. And it is going to change in such a way that the I will land at this location 1 0 and j will land at this location 1 1. And when I say land, I simply mean where its tip will land. The vector is not landing anywhere. It's a scalar. It has a magnitude that is scalar, and it has a direction that is oriented in a particular way. But when I say land, I mean the tip of the vector, the coordinates of the tip of the vector. So then the scaling factor will again remain the same. So the new landing position of I will be the new basis vector, and that will be scaled by -1. The new landing position of j will also be the second basis vector, and that will be scaled by 2. So that's why we had -1 times 1 0, which is this column, plus 2 times 1 1, and this 1 1 is this column. And as a result, we have the final VTRS. This is vector. This is the final vector after T for transformation, R for rotation, and S for shear, after rotation and shear transformation. So this is how you can actually visualize composite linear transformation in terms of what happens to the starting unit vector. So the starting unit vector undergoes 2 transformations. So just to recap this lecture before winding up, in the previous lecture, we had learned that a single matrix is a linear transformation function, where what the function does is it transforms one vector into another. So what does the matrix do as part of the function? It simply multiplies with the vector. So if a matrix is multiplying with a vector, it essentially means you are linearly transforming the vector. Now, what if a matrix is multiplying with another matrix of the same dimension? In that case, you can imagine it to be 2 composite linear transformations. So you can imagine it to be 2 linear transformations applied back to back. So whatever matrix is on the right hand side, that is the transformation that is applied first. So you read from right to left, not from left to right. So if left one is shear and right one is rotation, you are applying rotation first and shear next, not the other way around. And if any matrix, we can also decompose into multiple composite operations. So you can imagine that like it's essentially like distance versus displacement. So if you first rotate by -90 degree, then rotate by +45 degree, then again multiply by rotate by -45 degree, your total rotation in that case is -90 degree. But you are describing it as the sum of 3 composite linear transformations, which is -90 rotation, +45 rotation, and again -45 rotation. So any individual matrix can be decomposed into multiple linear composite operations. And a product of two matrices you should always visualize as composite linear transformation. So I hope this lecture brings you a new perspective into what happens to vectors when multiplied by one single matrix, what happens to a matrix when it's multiplied by another matrix, and what happens to a vector if it's multiplied by two matrices back to back, which is simply 2 times the vector transformed. So with that, we will wind up the lecture, and in the next lecture, we will again look at some more details of vector linear transformations. And the reason why we are spending so much time on linear transformation is because it is one of the biggest concepts that you have to understand thoroughly in linear algebra, because in neural networks and in transformers and many other architectures, we are essentially performing a lot of linear transformations from lower dimensional space to higher dimensional space, or vice versa, or sometimes the dimensionality is retained. So try to understand this very thoroughly. If you'd like to watch this lecture once again, feel free to do so. But we'll be meeting again in the next lecture. Until then, take care and bye.